Okay, we're continuing to talk about heat transfer. In the last video, we talked about conduction. That's the way heat travels through solid objects. And we're going to move on now to convection, in which heat flows by the mass movement of molecules from one place to another. So it's actually traveling through a fluid like air or water. So it could be through the movement of water molecules here. As we heat up the water, these molecules are going to move and swirl around and mix together with other cooler temperature molecules, and they will collide with them and transfer their energy to them and heat them up. So that's an example of convection. Or the hot air in a furnace swirling around with the cooler air mixes together and transfers its heat. So many home heating systems, especially in our area, are hot air systems where a furnace heats the air and blows it out of a register that mixes with the cooler air and heats our homes. And our body temperatures are regulated by blood, which transfers heat on the skin. So sweat, the evaporation of sweat cools us. We talked about that in a previous chapter, the cooling effect of evaporation. And if we move on to the third way in which heat can be transferred, it's radiation. So there is no air or fluid or solid material between us and the Earth. In outer space, it's just a vacuum. So how does that heat get to us? And the answer is it's radiation. Electromagnetic radiation is like an energy wave that can travel through space and brings us the heat from our sun. And it radiates temperatures. The sun is a whopping 6,000 Kelvin. And when you think about it, almost all of the energy on our planet in some way comes from the sun. The burning of fossil fuels, for example, those fossil fuels were once living things like dinosaurs or prehistoric plants, and those plants grew based on photosynthesis from the sun. Really, everything can ultimately be traced back to the sun in terms of energy that we use on a day-to-day basis. So radiation is perhaps the most important method of heat transfer in a way. So Boltzmann here, we have seen Boltzmann before when we learned about the Boltzmann constant when we were looking at the ideal gas law. But that's not the only constant he's known for. We also have this lowercase sigma, which is the Stefan-Boltzmann constant. So again, this is a constant value of 5.67 times 10 to the negative 8 watts per meter squared times Kelvin to the fourth. And this constant, this Stefan-Boltzmann constant, can be used in this equation to determine the heat flow in terms of energy per time due to radiation. So it is epsilon times sigma times alpha t to the fourth. So the sigma, we've already said, is this Stefan-Boltzmann constant. It's just always that number. Area A is area, and T is temperature in Kelvin. We have to be sure we're using Kelvin because that's what's going to cancel out with our Stefan-Boltzmann constant. And that just leaves this epsilon. What is this? This is a new variable we're introducing. It is emissivity. And so it's a characteristic of the surface that is experiencing the radiation. So if you've ever left some things out in the sun, that are different colors. You may have noticed that black objects tend to get hotter more quickly, and that's because they have a higher emissivity, close to 1, whereas shiny things like aluminum foil have an emissivity of nearly 0. They're going to reflect that heat and not absorb it, where the black stuff does absorb the heat. This is one reason why, especially in hotter climates, fewer and fewer roofs, flat roofs, are being made with black materials, because that's going to absorb the sunlight and increase the air conditioning load on a building. More often you see flat roofs being made with white materials that have a lower emissivity and will reflect the sunlight and reduce the air conditioning load on that building. So again, the textbook author likes to tie in these physics concepts to the health field. And so your body radiates heat, and if you're in a cold environment, you are radiating more heat than your internal body chemistry can produce. And so one way that the body copes with that is to start shivering. Why do we shiver, if you've ever wondered about that? Shivering actually forces your body to move involuntarily, which increases the metabolic rate, which increases your internal temperature. Now that'll only warm you up so much. The best thing to do is wear warmer clothing, which insulates that heat and keeps it from leaving your body. The clothes or blankets themselves don't generate the heat, they just insulate the heat. Another thing you may have seen is runners at the end of a marathon being covered in mylar, and that is a very shiny, a shiny material which would have a very low emissivity to reflect in the heat that would otherwise be radiated out of the person. So one additional thing that affects the rate at which a material will absorb heat from radiation is the angle at which the heat is being exposed to that surface. So for instance, here we have a sunbather, and the sun is not coming directly down on top of the person. Instead, it's coming at an angle. And when the sunlight, when those rays come at you at an angle, you're not exposed to as much of that radiation. You're actually, if we kind of made a right triangle here, you would be experiencing the vertical component of that vector, which is a little bit shorter than the full magnitude of that vector, which is the hypotenuse of that right triangle, and the hypotenuse is always the longest side. So this vertical leg is going to be somewhat shorter. So in this case here, our heat flow over time is going to equal 1,000 watts per meter squared times the emissivity of the surface times the area of the surface times cosine of theta. So this equation here is specifically for the sun's rays. It's not a general equation for any type of radiation. It's specific to the sun. And so let's look at an example problem using that equation. We want to know what is the rate of energy absorption from the sun by a person lying flat on the beach on a clear day if the sun makes a 30-degree angle with the vertical. Assume that the emissivity of a person is 0.70, and the energy per area, watts per square meter of the sunlight, is 1,000 watts per square meter, and the area of the human, in this case, is 0.8 meters squared. So our angle here is 30 degrees. It said that the sun's rays were making a 30-degree angle with the vertical. Okay, and by a little bit of geometry, we can see that that's 30, and this is 90, then this will also be 30. So that theta is 30 degrees. If we look at our equation here, Q over T equals the 1,000 watts per meter squared. That's the full energy of the sun per area, times the emissivity of the person, which was given as 0.70, multiplied by the area of the person, which was given as 0.8 square meters, and then we're going to multiply that by cosine of theta, which is 30 degrees. So the heat flow per time being absorbed by this person is 500 watts, which is 500 joules per second. So this idea that the angle at which the sun's rays strike you affects the amount of energy you absorb is what's responsible for our seasons. So the Earth's axis is on a tilt, which means in the summer we are tilted towards the sun's rays, and so when we're tilted towards the sun, the like right here at this level, that angle between the tangent part to the Earth and the sun's rays is perpendicular. So the angle theta is pretty much 0 here. So at this level, when it's facing the sun, you're seeing the majority of the sun's energy. As you're tilted away from it, that angle, okay, is going to be nearly 90 degrees down here at this most southern part of the globe. So you're getting very little of the sun's energy. So so the part that faces that gets the sun's rays full on, that's going to be very hot. As we know, equatorial regions of the Earth are generally much hotter than the poles down here. This is close to the southern pole. It's going to be very cold. And down here, it's going to be wintertime. Up here, it's summertime. So it's not only the distance down here is farther away from the sun, but it is also to do with the angle that those rays are hitting the Earth. And again, another way to tie this into the health and medical fields are thermal imaging. Measures the radiation, the heat that is radiating off of these people, and that can be used for medical imaging to look for potential health issues, tumors, infection, poor circulation. Of course, the thing this reminds me of is the movie Predator, in which the alien villain or hero, I suppose, depending on your point of view, used a thermal imaging to detect his prey in the jungle. So that's just a interesting little bit of trivia. That brings us to the end of chapter 14, the end of our heat chapter, and very nearly brings us to the end of the semester. We have just one more chapter to go, and I'll start that with the next video.